All right, next I want to talk about what are called degenerate linear transformations. What I mean by that is I just want to think about the following. So I want to think about, let's go back to me just giving you the linear transformation, say xy. And what this is going to do is I'm going to send this vector xy to the vector 4x plus 2y and 2x plus y. Okay, so that's going to be our linear transformation. And I want to think about what's going to happen to the unit vectors 1, 0, and 0, 1. So I just want to play around with this just a little bit. So 1, 0, and 0, 1. And let's think about what's going to happen here. 1, 0 is going to be sent to the vector 4, 2. And 0, 1 is going to be sent to the vector 2, 1. And so if we were to graph this, if we were to have our normal Cartesian plane, we would have our vector 1, 0 and our vector 0, 1. And 1, 0 would be sent to the vector 4, 2. So I'm just going to estimate here, but that's roughly going to look like 4, 2. Okay, it needs to go through the origin though. So there's 4, 2. And our orange vector is going to be sent to the vector 2, 1. So it's actually going to be the same vector that we had before. Instead of 4, 2, it's just 2, 1. So it's going to be half the length, okay, of that vector. And let's think about if I were to pick any arbitrary point A, B, it would look like, we already know the general shape of the transformation, but if I were to have any point A, B, and I were to apply this linear transformation, what happens is you're going to send this to 4a plus 2b, comma 2a plus b. And what that's going to do is this is really, you're multiplying by the matrix 4, 2, 2, 1 times AB. That's really how we should think of the linear transformation, is multiplication on the left by that matrix. And what's going to happen is whatever vector you start off with, you're going to multiply by that matrix 4, 2, 2, 1. Okay. And so let's just pick one more arbitrary vector. Let's say negative 1, 2. Okay, so that's going to be, I'm going to use a purple color here, but we have negative 1, 2. Actually, let me pick, negative 1, 3. Okay, so let's pick negative 1, 3. And so that's going to be this purple vector, so it's going to go negative 1 and 3. So it's going to look, again, I want to use a thicker line just to be a little bit more forgiving, but that's going to look something like that. Okay, so there's our vector, negative 1, 3. And what I want to do is let's think about what does our transformation say is going to happen here. Well, we're going to get negative 4 plus 6 and negative 2 plus 3. And this purple vector is also going to be, it's also going to be sent to that vector 2, 1. Okay, and so it turns out what's really going on here is that all vectors, if you look at these, all vectors, the outputs t of xy are being sent to vectors of the form uv, where v is, let's say it a little bit easier, where u is 2v. So it turns out all of these are being sent to vectors of the form, so the images of all these vectors are going to be 2 times some other vector. So this would be 2v over v. So this is going to be, what I mean is v times some vector 2, 1. So all of our outputs are going to be multiples of that line 1, 2. And it turns out that no matter what vector you start with on the plane, it doesn't matter what it is, how big it is, in what direction, it's all going to be, once you apply the linear transformation, it's all going to be squished onto that one line. Now, why does this happen? Why is it that this linear transformation sends all the vectors onto that one line, right? This is a subspace not of 2 dimensions, but this line through the origin is a subspace of 1 dimension. What is going on? What do you think? What happens with this matrix 4, 2, 2, 1? Do you notice anything? What stubborn quality are we still we're still talking about this? What is the determinant of that matrix? It turns out that the determinant of that matrix, 4, 2, 2, 1, is 0. And so that tells us that our images are not going to be everything in R2. Okay, so we're not going to have everything in R2. Our determinant is 0, so that tells us that we're going to have either a 0-dimensional or a 1-dimensional subspace. Just for full clarification, the only transformation that gives us a 0-dimensional vector space is where T of V is just always 0. No matter what your input is, your output's always 0. You can think of this as always being multiplied by the 0 vector. Or by the 0 matrix, I mean. So you can always think of this linear transformation as T of V is just left multiplication by the 0 matrix. Turns out that's a perfectly valid linear transformation because 0, 0, 0, 0 so linear is a perfectly valid matrix. Everything's fine. It's linear. It has all the nice properties you want, except that it just happens to send every vector to the origin. Okay, and again, this matrix 0, 0, 0, 0 is the only matrix where every vector gets sent to the origin. Okay, that's the only matrix where that happens. The last thing I wanted to say about this example is just think about 0, 0, 0, 0, and the previous example that we saw where we had left multiplication by the matrix 4, 2, 2, 1. Both of these matrices have determinant 0, and therefore their images are not going to be all of R2. Okay, but I just want you to think about what's the dimension of the image for our example 4, 2, 2, 1. So that's going to be just a line in R2, so that's a 1-dimensional image. And I also want to ask what's the rank of the matrix. And it turns out that the rank of the matrix 4, 2, 2, 1 is also 1. Okay, so rather curious. We'll talk much more about rank of matrices and linear transformations. I shouldn't say much, but we'll talk more about this. And the rank of 0, 0, 0, 0 is 0. Right, there are 0 non-zero rows. So the rank of that matrix is 0, and likewise, if you were to think about, this is going to be kind of silly to draw, but if you were to take any vector that you want, just whatever vector, its image is going to be the boring old 0 vector. No matter what vector you put in, doesn't matter what you start with, your output is always the origin. That's it. That's what this vector transformation does. Take any vector, send it to the origin. Okay? And the rank of the origin, the rank of the 0 matrix is 0. So we'll just keep those thoughts there. Okay? And we'll talk about that in a little bit more detail next time.